let's talk about the tools you rely on every day. You know, that hammer, that drill bit, that wrench. There's this incredible hidden science behind why they work, or why they sometimes fail. And it all starts with the specific material they're made from, tool steel. I mean, have you ever really stopped to wonder why a hammer can take an absolute beating without shattering, but a drill bit, if you just look at it the wrong way, can snap in a heartbeat? Well, that's not a mistake. It's actually by design. You see, the whole secret is in choosing the right kind of tool steel for the job. And believe me, it's not as simple as just picking something strong. It's a really calculated decision. It's a masterclass in engineering trade-offs. Okay, so let's get right into it. The first thing you've got to understand is that steel isn't just steel. It's a huge family of different metal alloys, and each one is engineered with its own unique personality for very, very different jobs. I mean, just think about the sheer variety of tasks we ask of our tools. A drill bit needs to cut, so it has to stay sharp and resist wear. A punch has to shear through metal, so it needs to be tough enough not to shatter. A plastic mold, that needs to be polished to a mirror finish. And a hammer? Well, a hammer just has to survive getting smashed into things over and over again. There's no way a single type of steel could possibly do all of that well. And that brings us to the core challenge, the big idea for any maker or engineer. We call it the great trade-off. Because when you're choosing a steel, you're almost always forced to make a tough choice between two essential and kinda contradictory properties. And what are those two properties? Well, they're wear resistance and toughness. So wear resistance is pretty much what it sounds like. It's the steel's ability to fight off getting worn down, to hold a sharp edge even when it's grinding against other stuff. Toughness, on the other hand, is all about absorbing a sudden shock or impact without cracking or just straight up breaking. Here's a really good way to think about it. Wear resistance is like a marathon runner. It's built for endurance, for going the distance. Toughness, that's your heavyweight boxer, built to take a massive punch and stay standing. Now, here's the problem. It's next to impossible to be a world-class marathon runner and a heavyweight champion at the same time. And the experts agree. One of them put it perfectly, saying, increasing wear resistance usually decreases toughness, while increasing toughness may deteriorate wear resistance. It's this constant balancing act. The harder and more wear-resistant you make a piece of steel, the more brittle it's probably going to be. Let's look at some real numbers, because this makes it crystal clear. Check out A2 tool steel. It has an awesome wear resistance score of 65, perfect for things that need to stay sharp. But look at its toughness, only 40. Now compare that to S7 steel. It's a shock-resistant grade. It has a monster toughness score of 103, but its wear resistance plummets down to 42. See? You gain in one area, you lose in another. You just can't have it all. So when you see those numbers, the challenge becomes really obvious. If there's no such thing as a perfect steel, how in the world do you choose the right one? Well, it's not a lucky guess. It's a system. You know, when a seasoned toolmaker has a problem, let's say a punch for forming metal keeps cracking, they don't just throw another material at it and hope for the best. Nope. They follow a clear, logical process to find a better solution. And that whole process really just boils down to 3 pretty simple steps. First, you define the application. What exactly is this tool going to do? Second, you identify the most critical property. Does it need to take a hit, or does it need to stay sharp? And then finally, you choose a grade of steel that's a champion in that one property you need most. Okay, let's put this into practice. A cold working chisel, the kind you hit with a hammer. What's the number one thing you need? Toughness, right? So it doesn't shatter. S7 is the obvious choice. What about a heavy-duty shear blade? Again, toughness is king. In fact, here's a great little rule of thumb. If the tool hits something, start by thinking about toughness. If it scrapes or cuts something, start by thinking about wear resistance. That one little rule will get you most of the way there. But hang on, it's not just about performance. You've got to think about the practical, real-world stuff too. Like, how easy is it to actually shape the steel into the tool you need? Some of these super hard steels are a total nightmare to machine. And then there's the big one, cost. The best steel in the world doesn't do you any good if it makes your product too expensive to sell. These things are absolutely critical. So, after you've weighed the toughness versus the wear resistance, and you've factored in the realities of cost and actually making the thing, you land on the real goal here, finding the perfect compromise. Because in the world of tool steel, perfection is basically a fantasy. What you're really looking for is the best possible fit. And if there's one thing to take away from all this, it's this. There is no magic, one-size-fits-all steel. every single choice is a compromise. It's a deliberate decision to say, okay, for this specific job, this property is more important than that one. But here's the real kicker. Even if you make the absolute perfect steel choice, your tool can still fail if the other parts of the puzzle aren't right. A great tool is always, always more than just the metal it's made from. You have to look at the whole system. Was the tool designed correctly? Does it have sharp internal corners that are just asking to crack? Was the heat treatment done right to actually bring out the steel's best qualities? And hey, is the person actually using the tool correctly? A failure in any one of those spots can make the best steel in the world look terrible. So what it all boils down to is this. The goal is not to find a steel that will never, ever fail. The real goal is to choose the most appropriate steel to have the fewest problems over the tool's entire life. It's just smart, practical problem solving. So I'll leave you with a little challenge. The next time you pick up a tool, any tool at all, just take an extra second. Look at it. Think about all those invisible decisions, all the compromises the maker had to weigh. What did they choose to prioritize? Toughness, wear resistance, maybe cost? What trade-offs are you literally holding in your hand?